Good morning. Welcome to the club night after party. So it is my great pleasure to introduce this morning's keynote speaker, Leah Somerville, Associate Professor of Psychology and faculty at the Center for Brain Science at Harvard University. Leah directs the Affective Neuroscience and Development Lab, and it's really my pleasure to introduce her because not only because of her work, but because she's a great friend of mine. And I just want to brag a little bit about Leah's accomplishments. She is a triple threat who's made significant contributions to cognitive neuroscience, social neuroscience, and developmental neuroscience. And for these, basically these contributions to the field, she's been awarded in the last 2 years the Early Career Award in each of these fields. So the Cognitive Neuroscience Society gave her the Early Career Award in 2017. The Social Affective Neuroscience Society just awarded her with the, I guess it's also the Early Career Award this year at the meeting in New York. And the American Psychological Association recognized her work also in 2017. So really, like I said, a triple threat. So Leah's work is supported by the Human Connectome Project, Typical Development, a large-scale consortium, and NSF Career Awards and various other grants. And as you'll hear about today, she works in the area of brain development, motivation, decision-making, emotion, and risk for psychiatric illness in development. So please join me in welcoming our speaker.
Well, thank you so much for having me. It's really such an honor to be here and have an opportunity to share my work. So thank you to the OHBM Program Committee for inviting me. Today, I'm going to describe our research that's really focused on the intersection of psychological and brain development. I consider myself a psychologist and a cognitive neuroscientist, so you'll hear a lot about behavior today in my talk. And I'm especially interested in the phase of life known as adolescence. This is a time that begins around the onset of physical puberty and ends around the time when an individual takes on independent adult roles in society. There are many reasons why we should celebrate adolescence as a phase of the lifespan. This is when individuals are making numerous kinds of gains and accomplishments in the complex behaviors that they're using to increasingly navigate the world in independent ways. But we can also consider adolescence as an important research agenda to understand better because of some of the unique risks that arise during this time of life. And these were previewed very, very nicely yesterday in Bea Luna's wonderful talk. So we're particularly interested in understanding this intersection of brain and cognitive development as it pertains to health-relevant behaviors. So despite these accomplishments and achievements that we should really celebrate adolescents for, they also have a unique suite of health risks attached to this time of life. For example, adolescence is the lifetime peak age of onset, window of onset, for a number of serious forms of psychopathology, which then predicts a reoccurrence across the entire lifespan. In addition to that, the top 2 of the top 3 causes of death in adolescence are preventable. They are the result of accidents, often resulting from adolescent drivers, as well as suicide. And so we can think of these sort of tragic consequences of adolescent development, of things that we might be able to better understand, the mechanisms that might lead some adolescents in that direction, with an eye eventually toward coming up with interventions and preventative measures. Adolescence is also a very active window of brain development. Of course, we've already heard some of this at this meeting, but I just wanted to summarize some of the broad-scale reasons why we can consider this a very important and active time of brain development. So for one, we see characteristic declines in gray matter that continue through adolescence into early adulthood. We see this across the entire cortical surface, and this trajectory is especially slowed or protracted in frontal association cortex, which is depicted in this cartoon diagram as sort of a flatter trajectory in the dark red. This is also a time in which white matter is growing and which is thought to promote more integration of especially long-range connections in the brain that integrate signal across many regions and brain systems. We can also think about adolescence as a time in which there's many shifts in network properties of the brain. This is a sort of vague way of describing it because some of the foundational work is still being done really to characterize some of the ways in which brain networks change through this time of life. And finally, at the cellular and molecular level, there are normative changes in neurotransmitter availability and receptor density. We heard some wonderful work about this yesterday in Bea Luna's talk about the dopamine system, and this occurs across a number of different neurotransmitters. So we can kind of think globally of adolescents, even though their brains are adult-sized, to be changing in dynamic ways which are presumed to influence behavior. So in my lab, we're really interested in understanding brain development to the extent that it can help us reveal some of the underlying sources of input that shape adolescent typical changes in behavior. And we study healthy developing adolescents for the most part with an aim to help reveal some of the foundational processes that are changing in order to inform health risks that may emerge during this time of life. And in particular, we're especially interested in emotional and motivationally relevant behaviors as they intersect with goal-directed actions and cognitive operations because they seem to exert a particularly interesting and complex influence on adolescent behavior. So in my talk today, I'd like to describe our work in the area of understanding how value influences goal-directed behavior through development, focusing on the transitions into and out of adolescence. And in doing this, I'm going to be highlighting the work of two trainees in my lab, my graduate student, Katie Insel, who's shown on the left, and my postdoc, Juliette Davidow, who are a real dream team, who I wish were here with me today to describe this work. So the question I'm going to focus on in my talk today is how do we develop a mature capacity to use value to optimize our goal-directed behavior? So just to unpack what I mean by this, we can think about value as driving our motivational processes. And we can define motivation as a sort of invigorating effect of that particular cues have over our behaviors, our thoughts, and our affective states. So things that hold value to us motivate us to act. We will be more prone to approach them. We will give things up in order to obtain them. We will work harder in order to receive them, and so on and so forth. So we could think of some ways in which this might play out commonly among people in this room. For example, traveling to Singapore, we might be motivated to sample the local cuisine, which might drive us out of the conference to explore the streets. As a graduate student, we might highly value obtaining, let's say, a PhD diploma, and we would potentially orchestrate our behavior in a way that will help us progress toward that goal. And of course, even if you already have your PhD, we all share the experience of being motivated to have papers, let's say, or abstracts accepted. And so we might orchestrate our behavior and work hard in order to achieve that goal. However, the relationship between value and goals is not just straightforward. On one hand, it's possible for value to guide our behavior in a way that's congruent with our goals. For example, if we were motivated to have a paper accepted, let's say we got to revise and resubmit a few days before the conference began, this might help us orchestrate our goal-directed actions, for example, to work diligently on the airplane on the way here, rather than getting sucked into watching the movies that are available on the flight. This is a particularly challenging one for me. We can also, though, think about ways in which value in the environment is incongruent with our goals, that it might drive us to act in particular ways that might actually have a negative impact on a goal that, or sort of disrupt us from achieving a different goal. So for example, if we had an early morning poster session, perhaps the alluring qualities of club night last night might have come into direct conflict with our wish to attend and be very bright-eyed and bushy-tailed for the poster session. So in this way, then, value can propel us toward goal-directed behaviors. It can also present a challenge or an impediment toward us being able to represent our goals and obtain them in a disruptive fashion. So fortunately, based on a number of decades of research using animal models, lesion studies, as well as human imaging studies, we have a good idea about the candidate neural systems that help us manage the use of value to orchestrate our goal-directed behavior. This occurs through dynamic interactions between complex, highly interactive brain systems that span subcortically to cortically, centrally involving the striatum, which is important to computing the value of actions we could take in the environment, orchestrating motor behavior through integration with the motor system, as well as interacting with a variety of areas of the prefrontal cortex that would represent a sort of broader goal state or demand on our cognition that would then, we can check these motivational forces against. And so we can think about the dynamic interactions and interplay among striatocortical circuit areas that are depicted in these diagrams to represent the integration of value with goal-directed actions. And so this is really going to be the central focus of the brain data in my talk today is going to focus on integration of signal within these systems. We can also, of course, observe these systems using human functional imaging. This is not necessarily developmental in nature, but we can use neurosynth to create maps for which depict areas of the brain that are commonly observed in studies about various different processes, of course. What I'm showing you here are three processes as they intersect and sometimes overlap. That is valuation processes, which you can see in blue, and two forms of goal-directed behavior I'm going to focus on in my talk today, that of cognitive control and learning, which are shown in purple and yellow respectively. You can see some key overlap areas, particularly in the striatum, that begin to integrate some signals relevant to these interacting processes. So in my talk today, I'm going to present three studies and then some current directions. The first two studies I'll present consider value as goal relevant and goal congruent, and asking how across development we fine-tune the ability to take value from the environment and use it to shape goal congruent actions in two domains, cognitive control and selecting what to learn. In the second part of my talk, we'll think about how value can be potentially disruptive to goal-relevant behaviors, and how we can take value signals and update them in a way that they no longer are disruptive. And then finally, I'll end with some current directions. So in this first study, we're going to consider cognitive control processes as a goal-directed set of behaviors, and then ask how the value or the stakes associated with performing these tasks shape participants' ability to perform well in these tasks, and then how the developing brain might interact with that. And so in particular, we're going to take a manipulation of stakes, which we can define as a sort of range of value that could come from goal-directed actions. So in particular, we could consider a high-stakes situation to be one in which the potential benefits and rewards are high, and the potential costs or losses are also high. So there would be a sort of large dynamic range of possible outcomes. We could consider low stakes to be a more constrained set of possible outcomes for which performance is less consequential. Now, work in adults has suggested that individuals can take cues about stakes from the environment and use them to flexibly upregulate behavior when it matters the most. So, for example, this is a task that is a simple interference resolution task, the details of which are not that important, but participants in this study engaged in this task under two conditions. One, when they were incentivized based on their performance accuracy, and one when they were not. When incentivized, participants perform both more accurately, which you can see on the right side, as well as more quickly than when they were not. And so the idea here is that the value cues from the environment were used and integrated to flexibly upregulate performance above and beyond what an individual would have otherwise done when value outcomes were not at stake. Now, this might be surprising, like why don't we maximize our performance all the time? But theoretical work in psychology has suggested that effort is costly, and so we optimally tried to titrate our effort depending on how important of an outcome is at stake. So to what extent do people across different ages do this when high and low stakes are at play? What we did was we asked participants of varying ages to complete a go, no-go task. Many of you are probably familiar with this task, but essentially what happens is participants are presented with a frequent cue, which they're instructed to press a button quickly to. In this case, we made our task about space and planets just to keep it interesting, but participants are instructed to press a button every time they saw the planets with craters, and to withhold those button presses every time they saw a planet that had stripes on it. So in this case, then, participants are selecting and executing their actions in a rapid-fire manner. And we embedded this task within two different contexts. The first context is a low-stakes context. Participants are cued ahead of time that this next set of trials will be paid out quote unquote, under low stakes. What that means is participants would earn 20 cents for every correct action, whether that's pressing or not, and they would lose 10 cents every time they made a mistake and made the wrong action. They then completed a block of trials and then found out at the end with performance contingent feedback how they did. Now we can compare their performance in that context with a high stakes context in which participants were instructed that they would earn $1 for every correct action that they took, and they would lose 50 cents every time they made the wrong action. They then completed a block of the exact same types of trials, and they found out at the end how much money they won or lost. So what we can do here then is compare the exact same task, but performed under either a higher or lower stakes context, and we can ask whether that influenced participants' performance and neural activity and connectivity. So what I'm going to show you first is behavioral data. We treated age as a continuous variable in all of our statistics, but I'm going to show you some binned data for descriptive purposes today. And on the y-axis here, we have D prime, which is a sort of conglomerate measure of overall performance accuracy, pressing when you're supposed to and not pressing when you're not supposed to. So first of all, when we look at the low stakes data, we see that as participants grow through adolescence, this is, by the way, cross-sectional data, so I shouldn't say that, but instead we see age-dependent patterns of change in which participants are performing significantly better and better with increasing age. This might seem like a really simple task, so it might be surprising to some that there are continued developmental gains in performance accuracy, but this task does go quite quickly, and so it's perhaps not surprising to see that there's a sort of fine-tuning of performance that is indeed continuing through this age range. We can then ask whether in high stakes participants amplified their performance above what they exhibited under low stakes. And starting with the oldest ages in our sample, we do indeed see a significant rise in performance accuracy under high stakes, as we would expect from the adult literature. Now, I want to take a quick detour and show you some new data we're working on that asks how it is that these participants are improving their performance under high stakes. And to do that, we can look at changes in reaction time. So what we're plotting here is how quickly participants press the button to the go stimuli, depending on whether it was the second, third, or fourth in a sequence of goes. Now, what participants typically do is, because the go stimuli are we ask participants to press quickly, and they're repeated in a sequence, participants tend to speed up over time. So they're sort of succumbing to a prepotent urge to press based on the frequency of these go trials. And you can see that under low stakes condition, participants are essentially succumbing to that prepotency and pressing more and more quickly, which makes then no-going potentially more challenging. But under high stakes, what these participants are doing is they're strategically slowing down their behavioral responses to the go cues with each additional go in the sequence. Now, each additional go in the sequence also means that a no-go trial is more and more likely to come up next. And so participants are showing a sort of strategic slowing that might be facilitating their performance accuracy under high stakes. However, this is a potentially sort of cognitively challenging state to be in, so they're selectively doing so when it counts. This prepotency effect, or sort of not succumbing to prepotency, I should say, under high stakes, is modulated by increasing activity in the ventrolateral prefrontal cortex, which is presumably helping participants implement this strategic shift under high stakes to help them perform better. So that seems to be what's going on in our oldest participants in our sample. What about the adolescent participants? What we found in this study was that we didn't find any evidence that the adolescent participants were improving their performance under high stakes. Rather, under high stakes, again, this is gains and losses, so higher gains and higher potential losses for incorrect trials. We see that our adolescent participants are showing equivalent performance that doesn't seem to be prioritizing their performance under high stakes. So, of course, I should also mention that we looked for this strategic reaction time slowing effect that we saw in our oldest participants. We saw no evidence that our younger participants were engaging in that kind of strategic shift. So, of course, we wanted to use our data to address in greater detail why. Why might adolescents not be amplifying their performance under high stakes? We had a few ideas, some of which were sort of implausible or not particularly interesting, but we wanted to collect data to try and rule them out. For example, we thought, well, maybe adolescents don't care about money. We didn't actually think that would be true, but we wanted to collect some ancillary data to address it. So we asked participants the subjective value of all the monetary gains and losses we use in this task. We found no differences across age. Even our youngest participants, although they didn't amplify performance under high stakes, liked and wanted the large amounts more than the smaller amounts. And the differentiation between the low and high stakes trials was equivalent across age as well. So the separation between these two contexts seemed to be consistent with age. Now, we also thought maybe participants who were younger weren't paying so much attention to the context that they were in. Maybe they didn't notice the cues or somehow not understand them, even though we instructed them well. So we wanted to do some analyses of sort of objective responses to seeing the cues that indicated that they were about to enter in to a high or a low stakes set of trials. So what we were able to do with our imaging data is isolate neural responses using fMRI, I should mention, to the cues that indicated that they were about to enter into a high stakes or low stakes context. And during this time, participants are not doing anything other than just noticing the relative value of the outcomes of their performance. And when we looked at the map that emerged from this analysis, this is all of our participants pooled together, we saw somewhat interestingly that many of the same brain regions that eventually get used to complete this go, no-go task are actually engaged in a preparatory fashion before they enter into high stakes compared to low stakes trials. So we could consider this almost an anticipatory response that's elevated under high stakes. And we thought, well, perhaps our younger participants were not engaging in this anticipatory process, which might call into question whether they were noticing or caring about the context to come. But we looked very closely and we found no age differences whatsoever in this map, which suggests that even our youngest participants were noticing the upcoming high stakes block. They were engaging in these anticipatory processes, but something about that did not translate into the moment while they were carrying out these go, no-go trials. And so we turned to looking at neural activity and connectivity during the task itself while participants were completing the go, no-go task to see whether we could explain the lack of amplification of performance in adolescence. So just jumping to the key finding, we wanted to ask whether the integration of signal within striatocortical circuitry differentiated between task execution under high compared to low stakes. To do this, we seeded the ventral striatum and we conducted a task-dependent connectivity analysis to ask what other brain areas are significantly more coupled with the ventral striatum, this valuation-relevant center of the brain, under high compared to low stakes. When we did this, we found just a very circumscribed set of activations, both in the left and the right ventrolateral prefrontal cortex, which is color-coded, and I'll explain that in just a moment. So what this connectivity finding means is that under high stakes, participants are amplifying the degree of functional coupling between the ventral striatum and the lateral PFC. Now, we were especially interested in this finding because, for one, it was predictive of behavior. That is, those participants who amplified their performance most under high stakes were the same individuals who were showing a greater degree of coupling for high relative to low stakes trials. And this pattern was also predictive of age. That is, the older the participant was, the more likely they were to be amplifying their performance under high, amplifying their relative connectivity between these regions under high stakes. So all of these observations put together allowed us to test for formal mediation, which was indeed significant, indicating that as age increased, there was a tendency to take stakes into account to flexibly improve performance when it counts the most, and this was mediated by the emergence of relative and selective connectivity that was amplified under high stakes. So these data suggest so far that corticostriatal coupling, as it is emerging in a relative fashion across age, seems to potentially be consequential for the capacity to take value and use it to guide goal-directed behavior. But so far, I've only shown this to you in one context, that is of cognitive control, and of course there are many, many other forms of goal-directed behavior as well. So we wanted to see whether this kind of framework would generalize to another form of goal-directed behavior, which is learning. So we asked participants to engage in a feedback-based learning task with either high and low stakes to ask whether individuals would prioritize high stakes in learning. So what happens during this task is that participants would see a pair of stimuli on the screen, in this case fractals that have different colors and shapes to them. They're initially completely neutral to participants, but over time, through trial and error-based learning, participants can figure out which of these stimuli is the optimal one to choose, that is, which would give a better payout most of the time. We presented participants with two value amounts at the top and the bottom of the screen, which indicated that one of the stimuli would pay out one of those amounts most of the time, the other would pay out the other amount most of the time. So in this case, we could play this task, and at first we don't know the value, which one is the optimal stimulus. We can guess maybe it's the green one, and then we'll receive feedback right away that tells us whether what that green stimulus paid out to us. In this case, it paid out 50 cents. And over time, you can figure out that was indeed the optimal choice, which most of the time would pay you out 50 cents. And you can figure out that the pink stimulus is the suboptimal choice because most of the time it would pay out nothing. Now, we had a variety of pairs of these fractal stimuli, so that, and this is an example of the high gain condition, but we also had a low gain condition in which participants were doing the same type of learning, but the differential value between the two outcomes was narrower, which would indicate it has sort of lower stakes attached to it. We also had loss trials where participants were learning to avoid losing money. So the optimal choice would be the one with 0, and the suboptimal choice would be one where you would actively lose. We're still analyzing these data, so I don't have the loss data to show you today, but I'd be happy to answer questions about them over email, and stay tuned for a forthcoming paper about that. So today, just looking at the high and low stakes gain data, we can compare learning performance to these two type of learning contexts. What I'm going to plot here is percent optimal choice, that is the proportion of time that participants ended up choosing the better stimulus, the one more likely to pay out a positive amount. And 50% here is in dashed line as chance performance. So first, looking at the low gain stimuli, we can see first of all that participants of all ages in our task did perform above chance. This is good. Participants were indeed learning and finding the optimal choice among the pair. We can also see a gradual improvement in that form of optimal choice behavior with age, suggesting again that there's a fine-tuning going on from adolescence into young adulthood that allows an individual to amplify their learning for these optimal choices. But critically, we can ask whether this, as our sort of baseline condition, shows modulation in learning for the high gain trials, which might indicate a stakes-based strategic use of value to amplify learning performance when it counts more. And we do see an age-based interaction in our data, whereby our earlier ages in this task show actually no difference in learning for the low and high stakes gain trials. But the prioritization of gain trials is emerging with age, such that the older you get, the more likely you are to sort of prioritize learning and select the optimal choice more frequently for the high relative to the low gain trials. Now, we are in the process of using computational reinforcement learning models to model the behavior in these data to get a closer look at the underlying computations that might reflect this prioritization of learning as it develops. We also collected brain imaging data during this task, and I can just give you a very quick, brief snippet of our first results. First of all, this task is highly, highly capable of driving up activity in the ventral striatum, as should be no surprise. This is a map looking at when participants selected the optimal choice compared to when they did not. And we can see robust increased activity in the ventral striatum bilaterally. Now, this is likely to be a product both of the sort of hedonics of selecting the optimal choice, but also of potential prediction error learning signals that could drive updating processes that would ascribe value to that advantageous stimulus. And we can ask, using an ROI analysis, which is shown here in the white segment of this activation that's depicting our region of interest, whether across our age span, participants are showing an elevation of striatal responding to the high relative to the low gain stimulus with age. And paralleling our behavioral findings, we do see that with increasing age, there's a relatively greater activity in the ventral striatum while participants are processing the high gain outcome and feedback data from the task. So this sort of parallels the behavioral findings, suggesting that this sort of flexible upregulation of learning is supported by striatal learning signals. Not surprising. Okay, so I want to switch gears briefly and describe one more study in which we're going to change the name of the game a little bit and instead look at times in which value is inconsistent with our goals and potentially disruptive to it. So we wanted to design a task in which we first, participants would acquire a value association for cues through learning. And then we wanted to transport those cues into a brand new context in which the instruction changed and flipped on them, and then to see how flexibly and rapidly they would be able to adapt their performance to these new set of rules. So what we did was we first, I should mention as well, this is in collaboration with Margaret Sheridan, who is at UNC Chapel Hill. So what we first did was we had participants come to the lab, and they first engaged in a reward learning task in which participants saw shapes that began out being completely neutral, and we instructed them to press a button very rapidly in response to these shapes, and if they pressed quickly enough, they would, for one of these shapes, in this case the circle, they would receive a monetary reward. So what's happening now is participants are forming a motor reward approach association in response to seeing that circle, so that it will motivate them to press rapidly, and then they will receive a reward for doing so. We have a control stimulus, in this case the triangle, in which participants see it just as frequently, and they're also instructed to press the button quickly, but for this stimulus they don't get any reward, they're just instructed to do that. So by the end of this reward learning task then, what we end up having are two stimuli with an equivalent sort of motor association history, one of which was additionally associated with reward for that approach button press. We then took those stimuli and ported them into a second task that participants did during fMRI, when those two stimuli became no-go stimuli in a go-no-go task. So now participants were pressing a button every time they saw new shapes, but every time they saw the circle and the triangle, which were those trained press shapes, now they were instructed not to press. So we flipped the instruction on them. And what we specifically wanted to know was whether the reward association that had been formed specifically to the circle would disrupt their performance or potentially facilitate their performance differently across age. So what we're seeing here then is how flexibly are individuals able to take those value associations that applied in one context and update them now that they're no longer relevant in a new context, and in fact would potentially disrupt them from performing accurately. So what I'm going to show you here is a plot of relative performance difference. So an upward going bar would mean that the reward history stimulus had better performance than the neutral one, and any down going bar means that the reward associated stimulus showed disrupted activity relative to the neutral one. And we're going to look at the data over time, because in this go-no-go task, now the instructions change, and participants have an opportunity, of course, to engage in updating of the value of that and motor association of that stimulus. So to ask how quickly or flexibly might individuals update their behavior over repeated experiences now that reward was out of the picture. So we see a complex age-related pattern of change, which was further modulated by time. So this is a complex interaction. Let me sort of walk you through it. What we see is with increasing age, there's an increasing tendency to be disrupted by the previous reward association. So participants are now engaging in false alarms and pressing when they shouldn't be, more so to the previously rewarded compared to the neutral stimulus. This was evident both in late adolescents and young adults, but this was further qualified by time, whereby the young adults by the end of the study essentially got over that association, and they flexibly updated their performance so that it was no longer selectively disrupted to the previously rewarded cue. By contrast, our late adolescents showed persistence in that reward association, selectively disrupting their performance, suggesting that the fine-tuning of sort of flexibly updating these behavioral repertoires might be something that's continuing to emerge relatively late in development. Now, we also saw in parallel to this behavioral shift, this flexibility type of pattern shown in our young adult participants, that this was also paralleled by enhancing connectivity between the ventrolateral prefrontal cortex and the ventromedial prefrontal cortex with age, which is the ventromedial prefrontal cortex is a key center for maintaining cash value associations, and so this could potentially, one interpretation would be that the adults are flexibly updating that process through cortical-cortical connectivity. Okay, to summarize what I've described to you so far, one thing to point out is that I think individuals of a wide variety of ages, I want to be clear about this, are capable of detecting and finding value in our environment. I'm not suggesting here that adolescents are newly observing or determining what is valuable to them in the environment. Even young children, infants, are able to figure out what it is that motivates them. However, I think one thing that's continuing to fine-tune throughout adolescence is the ability to flexibly use this information to guide their goal-directed behavior in a way that's increasingly optimal. This seems to also be facilitated by ongoing and continuing fine-tuning of the development of striatal-cortical system integration. Now, we've proposed this sort of as a framework in a recent paper that part of the figure is visible here. And what we're trying to demonstrate in this figure is that throughout adolescence, there might be a sort of expansion in the repertoire by which value would facilitate performance on a variety of goal-directed tasks, which is shown here sort of in the shaded area between these two lines. This would be an application of performance with value. However, this can't possibly be the whole story because, of course, the literature is much more complex than simply considering age as a factor that shapes when value can help and hurt our performance. There's many, in fact, studies that suggest that under some circumstances, even young children can use value to amplify their performance. And there are other studies that suggest that even in adults, there are cases in which value does not amplify performance. In fact, value can impair performance, seen in the literature on choking behaviors. So we've tried to sort of reconcile our data against other studies using very different kinds of cognitive demands and tasks to try and think about organizing principles that might predict when value can help and help us more and less. And so we're proposing an additional dimension to the development of this value-guided goal-directed behavior that has to do with how demanding the cognitive task is that's at play. So we're suggesting in this framework that for tasks that are relatively more easy, for which an individual sort of has facility over their performance and their performance is reaching mature levels, that would be a point at which value can begin to facilitate performance. And so for easier tasks, that could emerge earlier in development. Whereas for very challenging tasks, we think that it's possible that value could be constrained by ongoing development of the cognitive operations that would facilitate that process in the first place. So that with increasing development would be a sort of increasing repertoire of a variety of different kinds of challenges that value could facilitate goal-directed action. And there might be some tasks that are so difficult that value might never touch them. And so the general principle we're proposing here then is that value modulation would scaffold on the sort of the emerging capacity to perform well at a goal-directed task. This is something that's somewhat of a hypothesis at this point that we're explicitly testing in some ongoing work. Okay, so just in the last couple of minutes I want to describe some of the current and future directions of the work that we're doing. In particular, considering the approach that we've taken in all of the studies that I've demonstrated so far. All of these studies I've described so far have been carried out within the context of my lab. This work was somewhat hypothesis-driven and very specialized in the particular kinds of questions we were asking and the kinds of approaches that we took to address them. However, of course, we have to recognize that any given lab can only do so much in terms of the scope of the research that we have the capability to do. So I have to recognize, of course, that our data are constrained in the scope of investigation. One primary way in which they're constrained that I haven't talked about yet is that we've been treating age as a proxy for development. Of course, this is a decent proxy, but it can't possibly be the whole story because people develop at different paces and different trajectories with many, many factors that are endogenous factors that would influence developmental course. And we simply don't have the statistical power to detect the complex sources of development beyond just simply how old a person is. So we have to consider that as a fundamental limitation of the kind of work that can be done developmentally in many labs. So I think this is a place where the field is recognizing more and more that conducting slightly less specialized but more generalized and larger scope projects holds a real opportunity to help us sort of triangulate between these highly specialized, hypothesis-driven work and also more data-driven work that will allow for more complex models, for example, of the sources and mechanisms of developmental change. And so I've been really fortunate to be able to supplement the kind of specialized work I've described today with a more generalized and larger scale approach through my participation in the Human Connectome Project in development, which is ongoing. We've been collecting data for around a year and a half now, and we're well underway. Our data are being collected at 4 different locations across the United States, including Boston, Los Angeles, Minneapolis, and St. Louis. And we're hoping to really provide a resource for the scientific community to ask some of the more broad general questions about the sources and mechanisms underlying variance in development. So just to give you a snippet into what this project looks like, we're aiming to capitalize on the sort of successes that were gained from the Human Connectome Project that was conducted in young adults and extend our investigation into developmental populations. We are prioritizing connectivity measures in our functional imaging protocol, which I'll describe in just a moment. And in particular, the kinds of traits and processes and cognitive processes we're especially interested in capturing across development really prioritize sort of inflection points in behaviors and cognitions relevant to health in adolescence as well as childhood. We're also conducting work to modify and optimize processing pipelines in the HCP style in order to be appropriate for data that vary across age, including in young children. And we're going to make those tools as well as data publicly available, so I hope some of you might be interested in using the data. We're sampling approximately 1,350 different people from age 5 to 21. And most participants engage in this study in a cross-sectional way. That is, they come in once at one particular age. Those are all of the bars in red. We also have a longitudinal subcomponent that's embedded within this larger study that's especially focused on pubertal age development with a special interest in trying to decouple hormonal mechanisms that drive brain development during the transition through adolescence separately from those that are determined by age. And so a study large enough to do that might allow us to understand what developmental changes in the brain are more hormonally or age dependent. As you'll see, there's 2 different longitudinal cohorts. One focused on the entry into adolescence, which is shown in green. They return 2 separate times over the next 2.5 years. And then we have a second longitudinal subcohort that's sort of from middle to late puberty that's shown here in blue. We're collecting a number of modalities in this study, including a number focused on brain connectivity. This includes measures, diffusion measures of white matter, a bunch of resting state data, as well as 3 different tasks that constitute sub-studies in and of themselves, but also will allow us to isolate different brain systems that we could then investigate in a more targeted manner. And we're also collecting a lot of information about our participants, hours and hours worth of surveys and data collection about the developmental context in which they're growing up, including factors like life stress, family composition, and so on. We're collecting outcome measures relevant to health, including substance abuse, physical health, as well as mental health and well-being. And we have a hormonal collection battery that includes saliva and hair, and many, many more factors as well. So we're really excited by the possibilities that are opened up by this sort of more general and very large-scale study that will allow us to look at development in a more complex manner. I just want to highlight one way in which we can triangulate between the more specialized work and this more generalized work by describing very briefly 2 of the tasks that we have within the Human Connectome Project in development, which harken back to the themes that I described in the first part of my talk. So one of the tasks that we're using is a sort of twist on a classic reactivity task in which we can measure participants' responses to rewards and losses with a magnitude manipulation so that we can also look at scaling responses to relatively higher or lower stakes gain and loss processing. So what people do in this, they do a sort of incidental guessing task where they see a question mark, they make a button response, and they either receive win or loss feedback that's of high or low magnitude stakes. We also have an incidental conditioning procedure built into this task. You might notice that when participants win money, there's a circle surrounding their win feedback. When they lose money, there's a square surrounding their loss feedback. And then we take those circles and squares and we bring them into an inhibitory control task that follows it immediately afterwards. So very similar to how we looked at how early sort of reward associations might disrupt subsequent cognitive control, we'll be able to sort of test for replication of that effect in this larger data set, since the no-go stimuli in this task are ones that are either previously associated with reward or previously associated with loss. This second task also would have a sort of basic inhibitory control function for those who are not interested in previous learning effects as well. So just to end, we are going to be releasing our first wave of data next year, so please keep an eye out for that. Okay, so to close, in my talk, I hope I've emphasized how the value of being able to sort of triangulate between behavioral and brain development investigations to help us understand certain kinds of traits and behavioral profiles that are relevant to adolescent health. We're suggesting in this work that ongoing brain development is fine-tuning the way in which value can guide our goal-directed actions. And we think of this as a really adaptive, useful way for adolescents to exist. This is a time in which the greater independence of adolescents orchestrating their own goal-directed actions could provide key inputs and experiences to the developing brain to allow it to sculpt for complex adult roles. And so we think of this sort of ongoing fine-tuning as potentially a reflection of the experience dependence of brain development, which is sort of the optimal potential way that adolescents could exist in their time across the lifespan. So with that, I'd like to close by thanking my lab and funding sources. Thank you as well to all of the collaborators on the Human Connectome project in development, and thank you for your attention.